Okay, thank you, Mr. Sherman. Good morning. My name is Virginia Infante. I'm from Instituto Superior Técnico, that is an engineering university located in Lisbon, Portugal. And today I will talking about the effects of the friction stir welding parameters in the mechanical properties of dissimilar joints, namely using a plate of a composite with aluminum alloy. This study was performed by Arménio Correia, he's a PhD student, Paulo Santos, a master student, Daniel Braga, and myself, Virginia Infante. We decide to divide the presentation in four main topics. I will start with a brief introduction. After I explain experimental procedure, then results and analysis, and finally the conclusions. As you know, friction stir welding is a joining technology, is a solid state joint technology. Use a no consumable tool like this one with a shoulder and a probe or a pin, and we can weld join dissimilar materials with different properties. In this case, we can control the machine, the welding machine, in the vertical force, rotation direction, and travel direction. And we can see here the two plates. The first one, the aluminum alloy, located in this part, and the composite plate in another side. In terms of the proposed objective of the study and the explanation why we use dissimilar joints, the first one is because we can combine the different properties of the materials, we can obtain light structures, and of course sustainable structures. As I said before, we use two different materials. The first one is aluminum alloy 6082 T6, and we with 2 millimeters of thickness, and we introduce in the retreating sides in terms of the welding process. The other one is a glass fiber reinforced polymer with 5 millimeters. And looking for the mechanical properties, we can see that the thermal conductivity of the two materials are very, very different. 180 for the aluminum alloy and 0.26 for the composite. We combine different welding parameters. As you can see here, we use always 3 levels. For the rotation speed, we use 600 RPM, 800 and 1000. For the travel speed, 120, 130 and 140. And for vertical force, 150, 200 and 250. And we produce 9 different joints, combining, of course, the welding parameters. In terms of the results, static results, we can observe here that the 9 joints, it was performed. Why it was not produced? Because with the parameters used, it was impossible to weld. And looking for this result, we can see that the best result, it was obtained for the joint number 3 with these parameters. The worst it was for joint number 2. And we decide to analyze 3 different conditions, the best one, the worst one, and intermediate, to compare in terms of the fracture surface and in terms of the properties. Yeah? Okay, sorry. During the welding processes, we connect thermocouples to the plates, to the aluminum alloy plate and to the composite plate, and we obtain this behavior for joint 1, 2, and 3. Always when we observe an increasing in terms of the temperature during the welding processes, and another thing that we obtain the higher temperature for the joint that show us the higher values for the mechanical properties, for the quasi-static welding processes. In terms of the retreating size and of advancing size, the results is almost the same, but the advancing side show us a higher temperature in terms of the results. Looking for the macro and microstructure, we can observe different defects, voids and grooves. We can observe, of course, the interlocking between the aluminum alloy and the composite plate. This is the aluminum alloy, this is the composite. We observed a smooth line here that is, we can explain by the chemical adhesive. For the joint number 2, we observed the line without a regular interface, and we obtain a regular interface in joint number 1 and in joint number 3. We decide to analyze the chemical composition of the small layer here, and we observe that it's composed by aluminum and carbon. In terms of the fracture modes, we observe the different fracture surface, and the majority of the specimen, the fracture mode, it was in the composite side, like you can see here in the joint number 3 and joint number 1. The joint number 3 present 3 different fracture modes in the composite side, in the joint region, as you can see here, and a mixed mode composed by the 2 others. In terms of fatigue behavior, we start right now to perform the fatigue tests, and we obtain a lot of dispersion. We use, of course, the welding parameters for the best solution in terms of the quasi-static results, these ones, and we can see that this dispersion can be explained by the joint geometry and size, by the secondary bending moment. I have here a video, but I don't know if I can. Can I try? Just a moment. Where we can observe the secondary bending moment and, of course, the stress concentration at the joint transition. Concluding, as I said before, the joint strength is mainly obtained by the macro and micromechanical interlocking effects, but we observe also the chemical bonding in the both plates. We can also observe complex geometrical interface that tends to increase the mechanical interlocking effect, and of course the temperature during the welding process is very, very important and play a key role in terms of the mechanical properties of the final joints. Another thing, the solid state welding of materials with very different thermal expansion coefficient, the thermal conductivity, of course, implies different size and geometry of the defects, and also in terms of the Kinsing bond defects that we observed in the microstructure of the material. We observe also the thin interaction layer along the joints composed by the aluminum and carbon, and this is very important to explain the results. And finally, the fatigue tests. We are starting the fatigue tests right now. We should perform more fatigue tests, and we need to establish the welding processes. And that's all. Thank you for your attention.
Thank you.